Okay, everybody. How we doing? Thumbs up. Excellent. Well, it's a pleasure to see you all. In terms of announcements for beginning a lecture, I think there basically aren't any. There were a few people in my office hours yesterday, which was great because we just did most of the homework together other than the coding problems. So now the rest of you are behind. That's what you get because your instructor is lonely. So beyond that, I think, again, this class is on a very simple cadence. There will be, hopefully, we need to remember to post the weekly little quiz, but beyond that, your basic deliverables are just that, and the homework, which I guess is due this coming Wednesday, is that right? 2 Wednesdays from now. Thank you. Monday. October 6th is a Monday. Great. You guys should turn in your homework whenever it says it's due on the spreadsheet and ignore everything that I say, because obviously I can never remember. But basically, all your deliverables in this class are just homeworks and exams. So nothing too challenging. Any questions, comments, concerns before we get started today? Favorite color? Green. Great. Okay. So excellent. So today we're going to continue expanding our repertoire of problems that we can solve using a matrix to, I think, what is typically the sort of crowning achievement of your linear algebra course, which is solving the eigenvalue problem. This problem, unlike QR, which we basically managed to squish into one lecture, is going to take us a couple lectures to get all the way from 0 to algorithms that converge for this thing. And then we're going to consider what in some sense is an extension of the eigenvalue problem, which is this SVD factorization of a matrix. The reason for that is that what we'll find is that not all matrices have complete sets of eigenvectors. However, all matrices do admit an SVD, which is why typically in computational applications, the latter is I don't want to say more important because they're just different objects, but I think is a little bit more common, even though the former is what we all know and love from college linear algebra class. So today's lecture, I keep saying this, I think today's lecture will end up a little bit short. Our basic plan for tackling eigenvalues is as follows. So in today's lecture, we're going to talk a bit about computational applications of eigenvalue problems. Then next time, we're going to delve into making sure the eigenvalue problem is well posed. Like, do we have any business even trying to find an eigenvalue of a generic matrix? And then talk about some algorithms for actually computing eigenvalues. Those algorithms actually, I would consider to be kind of brain dead relative to what we did the last couple weeks. Like actually coding up LU factorization is mildly annoying. You might notice that I didn't do it in class, right? Like I kind of convinced ourselves that it exists and we can compute it in a particular time. But actually like extracting an LU factorization from a matrix or QR or whatever requires a little bit of coding, numerical stability, all that kind of stuff. Eigenvalue algorithms tend to be just like kind of dumb looking. Like take a vector and multiply it by your matrix a million times. This is also going to be a transition in kind of conceptual thinking in this class a little bit. So far, the algorithms that we've described terminate in a finite amount of time. And moreover, they give you an exact solution to the problem that you care about, modulo finite precision arithmetic, right? So in particular, when we do Gaussian elimination, QR, Cholesky, whatever, to solve Ax equals B, then the only error in solving that problem is due to the fact that we rounded in our arithmetic step, right? But the actual x that we extract when we run these algorithms is truly the solution to the problem up to those rounding mistakes. When we talk about eigenvalue problems, that's no longer the case. So in particular, eigenvalue algorithms are going to be our first example where we get successively better approximations to the solution of a problem, but we never solve it completely in closed form. Right? And in fact, one thing that you can double check is that it's kind of impossible to expect a numerical algorithm to terminate in finite time and give you eigenvalues generically up to precision. I'll let you think about that. There's actually kind of a fun problem there that has to do with equivalence to like algebra style thinking. So like in particular, you can design eigenvalue problems pretty easily that find like roots of really complicated polynomials. And so from that perspective, like roots of polynomials are hard things to compute with just like formulas, right? You might know that like, there's a quadratic equation, a cubic equation, a quartic equation, and then that's it, right? Fun fact from, Galois theory, I guess. But that aside, essentially sort of a byproduct of that argument is that the best we can do is approximate eigenvalues anyway. That's going to be basically the paradigm for the rest of this course. There's going to be very few algorithms we have from now on that just like terminate. Instead, you're going to have this new trade-off you have to navigate where like the longer you run the code, the closer you get to the solution of your problem, but you never quite get there, right? Notice that all of our discussion of conditioning in that case becomes even more critical because now we really don't expect our algorithms to get an exact solution. Okay. So in any event, before we talk about eigenvalue algorithms and all the fun extensions and so on, today we're going to have a bit of a shorter lecture. This is due to my reactionary thinking here, which is as follows. I also teach, well, used to teach the undergrad computer graphics course. I've taught machine learning a number of times. And here was the conclusion that I drew. Now, if I ask any of you guys to define an eigenvector, I bet you probably could if you've taken linear algebra course, right? There's a very famous equation. We've all written it down 1,000 times. Looks something like this. Ax equals lambda x, right? That defines an eigenvector. And then you're all programmed from your linear algebra class to work through all kinds of different techniques for finding these x comma lambda pairs. Most of the techniques you learn in linear algebra class are like wildly impractical from perspective of a matrix that's like larger than size 4, right? Like I think the typical thing people do is take the determinant of a minus lambda I, and then like that's a polynomial in lambda, and then start to find the roots. That algorithm is like the worst possible way to compute eigenvectors, it turns out. But it is one of very few that at least gives it to you in closed form for small matrices. So in this class, we're going to talk about completely different approaches that are more approximate in nature. However, before we talk about any of that, I think one of the big challenges I've encountered among at least our computer science students is as follows. All of you guys know this formula. Like I think if I blindfold you and send you to the room and ask for eigenvalue formula, you'd all come back with some version of this thing. But then the next question is, name for me one time in your life when you actually need an eigenvalue of a matrix. And what I have noticed is that the vast majority of our computer science students are unable to answer that question. And so essentially what we're going to do is spend a little bit of time in today's lecture giving you guys applications. Like, why does the eigenvalue problem arise so naturally? Like, it's not just like a fun trivia thing to like look for vectors where like multiplying by your matrix and scaling are kind of equivalent. But like that this is somehow a very natural problem that actually arises in optimization language a lot. One thing you guys might have noticed by now, my particular biases are two. One is I am a geometry professor, so we tend to draw lots of pictures. The other is that almost all of my research involves optimization problems. And so my bias is to try and take all of our linear algebra problems and kind of describe them in terms of different optimization problems you might want to solve. Right? For instance, we talked about least squares the last couple lectures and how all the matrix factorizations are sort of byproducts of the structure of that problem. So today we're going to talk about a different set of problems which basically involves a homogeneous quadratic objective function and a quadratic constraint, and we're going to see that that also leads to eigenvalue problems, and hence these things are actually pretty natural. Okay? If you don't know what that means, that's fine. You will by the end of the lecture. So essentially what we're going to do today is start with a few application-oriented problems and show that like it's really natural to expect PCA or, eigenvalues to actually solve that problem in practice. Oh, I gave it away. Okay, so to start with, we're going to consider like the world's most simple kind of data processing problem. This is almost like least squares, but not quite. So this problem is sort of a twist on our least squares thing, which is as follows. Let's say that I go out there and I collect a bunch of data points. In this class, our data points are going to have real numbers. We're not going to worry about like combinatorial variables. Okay. And so like for instance, I go around, I collect height, weight, blood pressure, heart rate. After of course doing all of my human subjects review and so on, and implementing ethical data collection policies. And so now I have a description of every person in my room as some vector, in this case in R4, right? Or maybe I can continue to add dimensions to this. Your height, your weight, your favorite color, I guess expressed in wavelength so that it's a real number, whatever. And now, most likely, the different dimensions of these vectors are correlated with one another, right? So for instance, I can tell you that as my age increases, you guys will experience this too, my blood pressure increases roughly proportionally. This happens because you people cause me a lot of stress. But in any event, these kinds of correlations, some of them are real, some of them are maybe spurious, but it's helpful to identify these things and even to quotient them out in a data set, right? So for example, a common thing that happens in statistics, not to put words in the mouth of whoever was teaching the class right before this one, is something called whitening, where you have a data set where there's like different correlations between different dimensions of your data points, and you kind of project your data down into some lower dimensional space where the correlations are fewer. Right? And so the basic procedure beneath that is something that I think we all know and love called principal component analysis. I think many of you have seen the formulas for PCA. And essentially my goal to start out today's lecture is to kind of justify why PCA really does look like an eigenvalue problem. I'm guessing many of you guys have even implemented it at home. But I think it's important to do this a little bit carefully. Okay, so here's our basic setup. We have a bunch of data points, xi, each of which is in like maybe n-dimensional space. Did I give myself notation? I did not. Great. So a bunch of xi, I equals 1 to, I don't know, what letter do we want to use for the size of our data set? How about big N? Okay, and this is a bunch of points in R little n that are describing like different patients in my medical experiment or something. Okay, does our notation make sense? Fabulous. So in the extreme case, maybe our data is just two-dimensional, and we just want to identify like the most important correlation in our data, like some one-dimensional thing, like that. So in this case, I've obviously drawn a very suggestive data set where the correlations we have in our data kind of follow some straight line like this. Right? So in other words, the horizontal and the vertical axis here are clearly correlated with one another. And our goal is to identify that. I think this picture looks familiar. I'm guessing many of you encountered this tool somewhere else. Okay, so how can we understand that? Well, one thing that we could do would be to identify some direction v in this space and kind of say, well, really, if I project all of my data along this axis v, then essentially that, in this case, one-dimensional projection explains my data pretty well. Right? I can like reconstruct my data set up to relatively small error. So let's codify that mathematically and see that it's going to lead us to a totally reasonable optimization problem. So in particular, here's our sort of model, is that each xi is approximately some scaling of an unknown v. So here, the scaling is specific to xi, and then I've got some vector v, which I don't know yet, right? Which is sort of capturing the main axis of variation in my data set. Does that story make sense? Now, notice this isn't quite least squares. It's not that I'm trying to predict x2 from x1. It's more that I'm trying to explain the variation in my data. Do we see that's a little bit different? So in particular, if I scale v up and down, notice that like the c's are just going to scale, I guess, down and up with the scaling of v. Right? And so what that allows me to do, oh, by the way, I can flip my slide here, is to add a constraint on my vector v, just to kind of narrow down the ambiguity in my problem. I might as well take v to have 2 norm equal to 1. That makes sense? Everybody agree with me? Do you see how this is already a little bit different than the least squares problems we've considered in the past, where now we have an unknown variable v, and we have a constraint, namely that the norm of our variable is 1. Okay? So what are we to do? So, right, so our problem looks like this. By the way, in the textbooks and the slide, I use little hats on our variable to denote unit length. If it's okay with you guys today, I might omit that on the board because I'm going to forget halfway through lecture anyway. So let's just do that from the start. Okay. So here's our model. We expect each xi to look roughly like some unknown ci times v. So at least so far, we've got two sets of variables, the c's and the v's. And we're trying to find the v that best explains our data. And so the question is, how can we model this using an optimization problem? Okay. So in some sense, I think a pretty reasonable thing to do, I think so, and so does like the last 200 years of mathematics, is to do the following. To sum over my data set, kind of inspired by my least squares problem, right? To look at each xi and to subtract off from it its projection onto v of xi, like that. And to look at that residual. If we go back to our picture here, notice that this, again, is a little different from least squares, which kind of measures vertical stuff. This is measuring like these distance to this curve, right? And what is it saying? Well, it's saying that a good v is one where if I project all my data points onto v, then essentially the difference between the projection and the original data point is pretty small. Okay? And now we have a constraint subject to mod v equals, oh no, not 0. It's equal to 1. By the way, somebody asked me at the end of class, I think I had an Australian undergrad linear algebra professor, and the phrase he always used was like mod for the length of a vector, but apparently that's fairly uncommon. I looked it up online yesterday. It is actually a thing. But if you're curious, that's what I mean. I think it comes from complex analysis, but I don't know. It's efficient. Okay, so does everybody kind of understand how we've taken our application-oriented problem and boiled it down to optimization language? Cool. All right. By the way, just a new little piece of terminology, and one that shows up more and more in fancy math. Oftentimes we'll call this a variational problem. Variational is just a fancy word for optimization. Okay. Variational calculus often involves optimization in spaces where your unknown is not just like a vector of numbers, but something like a shape or a function. In this class, that's not going to come up a whole lot unless we decide in our last couple lectures to talk about partial differential equations. If you like this kind of stuff, you should talk to your TA, Leticia, who's an expert on this stuff. Okay. So this is the optimization problem that we want to solve. Notice that the constraint, in some sense, does nothing, the way that we've written this problem down beyond, like, it doesn't really affect the optimal V, but it does, like, remove a scaling ambiguity. We should stop here. Is the solution to this problem, the way I've written it so far, unique? Like, I've removed scaling ambiguity, right? Like, I see some head shaking. What have I forgotten? You're making, like, a peace sign. I know you know the answer, but I'm going to pretend like you don't. Somebody else? Yeah, like basically, if I flip the sign, S-I-G-N, of V here, the solution to my problem doesn't change. No? Spoiler alert. If I flip the sign of an eigenvector, that thing is still an eigenvector. So we kind of see these problems are related to one another. Okay. So, right, so here's our like kind of pictorial version of this story. We'll also come back later to the version where there's more than one principal axis, but for now we'll just consider one. Okay. So, right, so here's our optimization problem in a different language, which is C. Conveniently for us, in our previous lecture, we actually derived a formula for CI. Does anybody remember what it is? It's actually quite simple in this case because V is unit length. I know you guys know. This is like undergrad stuff. Dot product, thank you, thank you. I appreciate it. So in particular, notice that CI here is just the dot product, wrong class, XI dot product V. Cool? All right. So now, finally, we can write our optimization objective function and then start doing a bunch of boring math until we recover the problem we want. Okay? So let's do that. So in particular, right, so here's our little formula so far. Oops, oh no. So let's do a little bit of simplification. So here's our expression. We have the sum over all our data points I of xi minus the projection onto v of xi squared. And as our colleague has suggested, I can write that slightly differently as xi minus, well, we've got v dot xi times v. Cool? By the way, if you watch my lecture videos from the last time I taught this course, for some reason I put an X there because teaching is hard and it's hard to be critical when you're at the board. So that's my bad. Okay, so really quickly, by the way, like this looks like a least squares problem. One could reasonably ask, like, you know, do I really need V here at all? Or rather, do I really need the norm constraint on V? And I would argue that like there's a couple different reasons why that's probably the case. In particular, notice that like this problem looks like least squares, yeah, but it ain't. Even if I drop the norm constraint on V, do you see why? There's actually two V's in this expression that get multiplied together, right? So if I think of this as a polynomial function of my unknown variables, what is the degree? Like least squares problems are degree 2 because it's squared. Think carefully. You're making the right gesture. Here, help me out. Louder. 4. That's right. This is a degree 4 problem. Do you see that? Because there's a product between V and V, and then the whole thing is squared. So actually, least squares is irrelevant here if I drop the constraint on the norm of V. So the constraint on the norm of V actually does two things. One is it reduces the ambiguity in my problem. Another is that it actually is going to allow us to make this problem tractable, because we don't know how to solve degree 4 problems in this class yet, or ever. Turns out those are hard. Okay. So, yeah. So, and in fact, right, well, never mind. Okay, so let's take this expression and expand it out and see what happens, as one is want to do. So, anytime I was in my office hours, I feel like I repeated the same thing like 8 times yesterday, which is like, anytime you see an expression like this, it is screaming out for you to expand the product out and see what happens, right? And so let's go ahead and do that here. This is going to end up being the sum over I of the norm of xi squared minus 2. Notice what's going to happen. I have v dot xi, then I'm going to have an xi dot v, right? So this is going to be xi dot v squared plus, okay, so this is v dot xi squared times the norm of v squared, right? That's our sort of quartic piece. What's the norm of v? It's 1. Yeah. Okay, so that means that we can actually simplify our expression a tiny bit more. This is the sum over I of the norm of xi squared minus xi dot product v squared. Okay. Now we're cooking with gas, because now our problem looks like least squares. But it ain't, because we have a norm constraint. Everybody with me so far? Cool. Moreover, is this term doing anything? No, right? Because the unknown in my problem is v, right? So this is just some additive change to my objective function. Okay. So really, I can think of it as some constant that I don't care about minus the sum over I of xi dot v squared. Okay, so now I'm going to do something that I think is pretty common. I think even in your first homework we did this, which is I'm going to take my entire data set and I'm going to stick them in the columns of a matrix. I think in this class and in my textbook I tried to be consistent and always put data sets as columns of a matrix. I realize that some software implementations don't do that. So in particular, I can define x to be like x1, x2, and so on, like that. Okay? Now, why might I do that? Well, remember we had this nice version of dot products where I kind of like I go this way across the rows of a matrix and down v. So notice that what is x transpose times v? Well, this is a vector where you have x1 dot v, x2 dot v, and so on. Does that make sense? Okay. So this is just like our fun little thought bubble here. So in particular, now we can write a really slick thing. So this is the sum over I of xi dot product v. Notice that the xi dot product v's are basically just the elements of this vector. So if we put that all together, we're going to get that this is some constant minus the norm of x transpose v squared. Cool? By the way, if you're a statistician, like you might know that there's an equivalence between, what is it, minimizing variance and maximizing, oh God, I'm forgetting the phrase. It's maximize variance, minimize bias, maximize variance, and what's the other one? Yeah, minimize. Anyway, whatever it is that statisticians care about, it's looking at you right here, right? We started with the minimization problem, and now we're maximizing something. This is an expectation, but I don't. There's a particular phrase I'm forgetting. Sure, minimizing error, maximizing variance. Those are equivalent, and basically that's what we proved here. There's some slick statistician phrase that I'm forgetting at the moment for this. Okay, so in particular, what we have argued, oh, and by the way, this is, of course, equal to constant. Notice that basically this class has like 2 math tricks that we just use over and over again. We have something squared, so of course this is v transpose x, x transpose v. Cool? Cool. Okay. So, what are we to do? Well, basically, what have we shown? We have shown that our optimization problem is equivalent to another one, which takes the following form. Gosh, minimize, it's not bias. Bias variance trade-off is something else. Anyway, that's gonna drive me nuts. Okay, right. So basically what we've shown is that our optimization problem is equivalent to maximizing over V, V transpose X, X transpose V, subject to the constraint that the norm of V is equal to 1. Sure. What Hamid said. Okay. So despite your instructor like mumbling to himself a bunch, hopefully we see the equivalence of these problems. And in particular, notice that like we're somehow in like better shape than we were, because we now have a quadratic function instead of a quartic one as our objective. And okay, like the way I've written it isn't quadratic because of the square root, but now it is. Okay. Notice this is a fundamentally different problem than the least squares problems we've talked about so far in this class. And really the reason that I'm like doing this in such boring detail is I want you guys to develop a code book. Do you see that? Like, oh, least squares. Well, that's like a linear problem and there's normal equations. Here I have a quadratic objective function with a quadratic constraint, both of which are the objective function is homogeneous, meaning there's no linear term. Right? Like if I added to this like V transpose B or something like that, like I had in least squares, then it turns out our math isn't going to work super well. Exercise left to the reader is how do you solve that problem? Come talk to me because I've written research papers on that. But in any event, if I have a homogeneous quadratic objective with a quadratic constraint, that is going to lead us to eigenvalue problems. That's what we're going to prove next. Okay? So that's the pattern matching that I want you to do. Like essentially least squares, we didn't have any constraint on our vector. Here we've added a constraint like that the norm is 1. And now this is going to lead us to an eigenvector problem. We don't know that yet. Spoiler alert. Any questions so far? By the way, one thing that like I want to just keep distinguishing this problem from what we've done so far. Let's say that I dropped the constraint because like I like least squares problems. What would be the minimum in this form? Yeah. V equals 0, right? And that wouldn't be too fun. So really this constraint is playing a really critical role here. Okay? So what are we to do? We have a constrained optimization problem. We want to describe how to solve it. And since this class does the same boring math like 18 times over, anytime we have an optimization problem, we should take its derivative and set it equal to 0. But sadly for us, we have a constraint, so we need to construct this thing we call the Lagrangian. So in this particular case, the Lagrangian is going to be a function of V and some Lagrange multiplier lambda for our constraint. Yeah? Hopefully the story is becoming familiar. This is the kind of thing, if you just practice 1,000 times, this isn't so bad. We've got V transpose X, X transpose V. Let me see if I can manage to guess the sign correctly. 1 minus the norm of V squared, like that. Make sense? All right. For mathematical convenience, no, I'm not going to do mathematical convenience. I'm going to solve this problem like this. Because I like to differ from the book and then get myself confused when the thing I write down on my notes doesn't agree. Okay. And this stupid tablet isn't working. Okay, great. So now that we have written it in this form, we can take the derivative and set it equal to 0. So what are we going to get? 0. What is the gradient with respect to V of V transpose X, X transpose V? Hopefully we know the answer because we've done least squares problems a billion times. Somebody knew? Literally anybody other than the two guys that keep answering? I know you guys know the answer. Hamid's got like a little smirk, so now he's going to tell me. What's the gradient of this thing? Two X transpose V. Thank you. This goes faster if you put me out of my misery. Okay, and what is the gradient of the norm of V squared with respect to V? Yes? Yeah, that's right. So 2 lambda V. Okay? So from this expression here, we can conclude, ta-da, X transpose V equals lambda V. Cool? All right, so what did we do? We started with a problem involving projecting data points onto this unknown vector V. We did a bunch of arithmetic. We got it to a form that looks like a quadratic function with a quadratic constraint, right? And now we take the gradient of that, we stick it here, and notice that this is just the Lagrange multiplier condition for the optimization problem, it is also the definition of the eigenvalue problem. Yeah? So if you're ever like wondering, like, where do eigenvalues come from? Like 82% of the time, it comes from some proof that's basically isomorphic to what we just wrote on the board. Like that essentially you have something that's like minimizing a projection, you have a unit norm constraint somewhere, and then this is just what falls out. By the way, if you wanted to make it look like these squares and you added a linear term like that, essentially what's gonna happen is you now have like a b somewhere in there, right? And that becomes some new thing. The name for this, which is really fun, I think it's cute, it's called a secular equation, which is an odd piece of terminology left over from a different time. So anyway, I'll let you read about that at home. Okay, so, yes, me here. What is the norm on V actually doing? Well, if it weren't there, then the problem would have a trivial solution. Absolutely. This is a great question. So like, what if I made the norm of V equal to 7? Right? Totally reasonable question. For one thing, in principle, we would need to modify our objective a little bit to account for that. But it would end up being kind of a scaling, so that's not a big deal. However, okay, so what would change in that case? We would insert a 7 here. What happens if you take the derivative of that expression with respect to V? Nothing. Yeah. Okay. Any other questions? That's good. You guys should be testing the boundaries of the argument that I just made. If you haven't figured it out by now, like 85% of the time, make a mistake. Cool. Are we done? So I think many people would say, yeah, you just made eigenvalue problem. But I think there's actually a reasonable detail that often gets neglected in this discussion, which is the following. So XX transpose is a symmetric matrix. One thing you may remember from linear algebra class, we're going to review this in our next lecture, is that symmetric matrices have full sets of eigenvectors. So if you have an n by n matrix, then you have n eigenvectors, right? This is the spectral theorem, and you should all go home and try to prove it. If you haven't, it's like a fun, way to, it's actually quite challenging to prove carefully. And a good application of Lagrange multipliers, incidentally. But that aside, or actually I think there's a topological argument to this one that's kind of fun, I remember reading. Basically, my point is we don't know which lambda. There's more than one lambda that satisfies this expression, right? So one thing that we could do is just go back to our objective function here and say, well, now we know something more about V, right? We know that it satisfies this expression. So in particular, V transpose X, X transpose V, well, we just showed that this entire thing I've braced here is lambda V, right? So in particular, this is lambda V transpose V. This is dot product of V in itself. V has length 1, so this is lambda. Okay? So we actually know two things. We know that the optimal V satisfies this expression, and moreover, at that particular point, the objective value you have is just lambda. So if we put those facts together, which eigenvalue do I want? You want the largest eigenvalue of X transpose. Does that make sense? So that's actually really critical. I think when you guys make arguments about this stuff, if you stop here, your answer's wrong. you really need to say like which eigenvector and why. Yeah? And usually that's as simple as just plugging back into the objective function and then making a short argument. Okay. So right. So does any questions about this little derivation? I mean, essentially, this is what we showed, and this object is called the first principal component after your data. When we talk about the SVD, we'll see that basically if you extract more than one principal component by something called the Eckert-Young theorem, that's exactly the same as basically adding more than one V here and a constraint that they're orthogonal to one another. Yes? That's a good question. Yeah. Is there a geometric interpretation for this object? Yeah. What do we think? Yeah. Yeah, this is covariance matrix. So in some sense, the elements of this thing, assuming you centered your data, what is it doing? It's kind of measuring like how the different dimensions of X correlate with one another, which if you think about it is sort of exactly what you're trying to capture in this kind of problem. Yeah, good question. Any others? Cool. Okay, so essentially, why did we do this example? Well, I want you to build a code book of optimization problems in this class, and then like basically your job in life and on the exam is going to be to look at problems, boil them down to one of these many problems in our codebook. Oh, my back. And then from there, I mean, the vast majority of numerical algorithms is basically a small wrapper around a piece of code for eigenvalues or least squares, right? And it's just a question of making that argument and doing that reduction. So in particular, what is our codebook so far? Well, we actually have quite a few optimization problems we know how to solve. So for instance, okay, let's say that A is positive definite, and I have an objective function which is quadratic like this, right? Then essentially what we've shown is that then AX equals B, just by taking the gradient, if we solve an optimization problem of the form AX minus B for some non-square A, we have shown the normal equations. And now we've just added a third thing to our repertoire, right? Which is essentially now a constrained optimization problem of 1/2 x transpose A x like that, where A here is going to be A is symmetric and positive definite, right? Like notice that XX transpose falls into that category. Then now we have AX equals lambda x. So hopefully you're starting to see that basically all of these problems that you know and love from linear algebra map really cleanly onto optimization, right? And that's going to be important because later on in this course, what are we going to do? We're going to derive algorithms for optimizing just generic functions f of x. And then one thing we can do is derive an entirely new class of algorithms for numerical linear algebra that basically plug in these different sort of canonical forms and then just say, like, what do those algorithms look like in this particular case? So for example, gradient descent, I think, is the obvious one. In fact, just for fun, let's write the gradient descent algorithm for optimization. I think at this point, most students have encountered some version of this thing if I want to minimize a function f of x, right? So the gradient kind of points downhill. If I want to minimize f of x, I could take a small step down eta times this thing. Let's say that I wanted to use it to apply least squares. Well, that leads me to a very particular iteration. Let's see, maybe the gradient of this thing, so that's going to be A transpose A x minus A transpose B, like that. This is actually some other algorithm for solving linear systems. In fact, you can say a lot about it, right? Because you can derive the Lipschitz constant of this thing from the form of A. So anyway, this is just a bit of a preview looking forward in this class. Like essentially what we're going to do, we start out with linear algebra algorithms that just care about specific linear algebra problems. Then we kind of step sideways into the world of optimization. And then we're going to go back and reconsider all of our linear algebra problems to derive an entirely new class. By the way, looking forward just a little more, because now I'm all excited about this stuff. Here's a fun thing you can do for this particular problem. Typically, an issue in machine learning is what we call the learning rate, or the step size for gradient descent, like this eta constant. Let's say that I took the objective function for least squares, and I specifically plug in this expression as just a function of eta, right? So I'm like kind of looking along a one-dimensional line for what my next iterate of my algorithm should be, right? In some sense, that's what gradient descent is trying to do, right? It's trying to figure out how far to step down the gradient. And there's all kinds of cool, like, adaptive step size algorithms for doing that. Notice in this particular case, that's a quadratic function of eta. So you can just work out a formula for the optimal step size for gradient descent. Anyway, this is a preview for conjugate gradient algorithm. Sorry, I got totally distracted. We're talking about eigenvalues. Right, so in any event, any questions about our derivation of this PCA method so far? Cool. So essentially, what we're going to do, again, as a reminder in today's lecture, is just go through a bunch of different problems and show that, like, if I know the eigenvalues of a matrix, then I can solve these problems really easily. There's no shortage of these things. Another one comes from physics. So in one slide, here's like all of this is sort of the beginning and end of my understanding of physics, which is that we have F equals ma, and that, like, for springs, it's particularly simple. So like the force on a particle moving on a spring with 0 length is just proportional to the sort of vector from one to the other. Yeah. So in particular, if I combine these two things together, I get a pretty simple ordinary differential equation. So let's say that I take all of my unknowns. Like, I have a set of particles that are moving around under these forces. And essentially, I can think of them as a big vector x of t, which is in some space like r to the 3n, where n is the number of particles. Does this make sense? So like basically I take x, y, z, 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 and I just like concatenate them together into one long vector, right? Now, obviously, mass times acceleration is a pretty simple thing. So there's basically a matrix that I can pre-multiply x by that's going to give me that per particle, right? Where it's just a bunch of masses down the diagonal, right? So I'll get m times x double prime like that. Cool? Okay, and moreover, notice at least for Hooke's law, obviously this doesn't happen in reality, but it turns out that a lot of problems are well approximated by formulas of this form, so this is actually a pretty reasonable thing to do for short time. Essentially, I can view this as like some matrix A times my vertex position, right? So here A is like taking differences between positions of different particles in my system. Okay. And now in the textbook, I argue something that like is true, but then I thought about it this morning and I panicked a little because it's not actually terribly relevant to eigenvalues. I'll mention it here so that you guys don't get confused in the course notes, and then I think I'm going to revise the textbook because in the youth of it was an error of my youth writing this book the first time around and using this as a motivating example. But in particular, here's a very typical thing we can do, which is a trick that's going to matter when we talk about numerical differential equations, which is that like all differential equations are actually like first order if you believe in yourself, and if you change your dimensionality. So in particular, here's the thing that I can do. I can define a vector v as x prime. Yeah, I can certainly do that. And now I can write a new system of ordinary differential equations. This is on 6n dimensional space because I'm going to kind of stack v on top of x, something like that, which looks like the following: x, v. What's the derivative of x with respect to time? V, right? By definition. What's the derivative of v with respect to time? Well, v is velocity. So the derivative of velocity is acceleration. So what I get is m inverse a x, like that. It's sneaky, huh? So just in general, by the way, in ordinary differential equation, in some sense, you never have to derive algorithms for solving higher order things in time. You can just always use first order things in time. That's, of course, completely false because there are algorithms that are more efficient if you know that you care about a second order thing. So for example, leapfrog is a very common algorithm for this particular ODE. But it's absolutely the case that like if you have a first order ODE solver, like you're good, you can solve anything. If you wait long enough. So notice that I can write this in kind of a sneaky fashion. So what is v? Well, it's 0 and then identity like that times xv. And here we have m inverse a x 0. So what have I shown? That like even if I started with a linear ODE that was second order, I actually can reduce it to a linear ODE that's first order. And this argument, by the way, stacks. If you did third order, you could do a very similar trick. Does that make sense? Now, the reason I actually don't like this example after thinking about it a bit, the A matrix here is like symmetric and nice, right? Because essentially like equal and opposite forces on particles, all that good stuff. This matrix is not symmetric, so it's actually not a great matrix to solve eigenvalue problems on. And in fact, you're sort of guaranteed to get complex valued eigenvalues for reasons that we're not going to go into today. So the things that we're going to talk about are absolutely right, but like it's actually kind of a more complicated example than it seems on its face. So that's just like a bit of a mea culpa in the textbook. But in any event, I think if we step back, the higher level point is oftentimes we are encountered with differential equations of this form, which are just first order. Right? So like y prime equals b times y, where b is a matrix and y is some long vector. And indeed, even Newton's equations fall into that category, although actually, in order to solve Newton's equations using the method I'm about to outline for you, you would need to solve for complex valued eigenvalues, which is not great. So notice that like e to the I theta is like cosine plus I sine theta, right? And you kind of know that like springs in Newton's laws should like kind of look like cosines and sines. So that's where that's going to come from. In any event, if I haven't totally lost you, even if this is maybe not the best motivating example, there actually are many ordinary differential equations of this form that, for example, describe exponential growth, or heat diffusion is one that your TA thinks about quite a bit, that fall into this category. Generically, by the way, I can write y of t is equal to this really weird thing called TB, which is the matrix exponential. We'll come back to what that means in a moment, times y at time 0. Notice that like if everything were one-dimensional, this ODE certainly works out. And so actually we could use eigenvectors to solve this problem pretty easily. So for now, assume that B is symmetric. Again, for Newton's law, that's actually not the case. And my bad for putting that example in the book. It took me 10 years to realize that like that's like maybe not the best motivator. But in particular, let's say that B has a complete set of eigenvectors. Now, when I say complete, what I mean is that if I have an n by n matrix, I have exactly n eigenvectors, and they span all of our n. Okay? That's where things go wrong with this example. You can make it work with complex numbers, but it probably wouldn't be the best way to solve Newton's laws. We'll come back to that in a second. So, what does that mean? That means that basically I have a whole collection of vectors that span Rn and are of the form, maybe yi, b times yi is equal to lambda I yi. Okay? And moreover, the yi's span Rn, because there's n of them. Everybody with me? Cool. So what does that mean? I use really terrible notation in these slides. Okay, that's fine. Okay, so in particular, since these span all of Rn, notice that I could like take my initial conditions for my differential equation, and I can write them in the y basis, right? I could write it as a linear combination Ci, yi. I don't love this because I've used y to kind of mean two different things, but I'll stick with it because it's what's in the book. Okay? And in fact, I could do that at any time t. Do you see that? So like, I could solve my differential equation using whatever method I want, right, to get y of t. And then I could project it back into the y basis because they span Rn. And what I'm going to get is that y of t is equal to some set of coefficients Ci of t times yi. Does that make sense? Cool. So from this perspective, assuming things are differentiable, which of course one should not do, I can differentiate both sides. What is y prime of t? Well, notice the yi's are constants. They do not depend on t, right? Because they just depend on the matrix of my system. And so in particular, this is the sum of Ci prime of t like that. Does that make sense? But we also know that yi prime is b times yi, or y prime is b times y. And I can substitute the form of y a second time here, right? And I can get the sum over I of Ci of t times b yi like that. Make sense? Something? Wake up, please. Cool. All right. What's b times yi? By definition. That's what I hear here. That's what you people sound like. So it's lambda I times yi. Ugh. All right. Like that. Yeah? So in particular, this is the sum over I, lambda I, Ci of t, yi. Cool? Cool. Now here's the thing. Notice we have the sum of Ci of t, Ci prime rather, is equal to the sum of lambda I, Ci, yi. So what have I done? If I just like freeze t, I have a single vector, which is like y prime, and I've written it in two different ways, right? Written it in the y basis with these guys as the coefficients, and I've actually written it in the same basis as these guys as the coefficients. So what is this screaming out for me to do is to just match those things together. In particular, what I can conclude is that Ci prime is equal to lambda I yi. Oh, nope, that's wrong. Ci. Does everybody see that? Like basically I have a vector that I've written in the same basis twice, but with two different coefficients. But a thing that we know about a basis is that like You can only do that once. So necessarily the coefficients are the same. And now I'm in a one-dimensional regime, and I can just quickly read off that Ci of t is e to the lambda I t times Ci of 0, which gives me a way to evolve my ODE forward. So essentially, what did I just argue to you? I showed that if I know all the eigenvectors of B, then necessarily I can just read off solutions of my ODE by writing the initial conditions in the eigenvector basis and then kind of evolving each of the coefficients separately. Does that make sense? Okay. Now, this is a very expensive algorithm for solving differential equations. In particular, it requires computing a full set of eigenvectors, evaluating this expression, and then putting it all back. We're going to see that eigenvector computation is very expensive relative to what we've done so far. So this is probably not what you do in practice. What you probably do in practice, though, is maybe just compute the full. So notice, for example, let's say that all the lambdas are negative, which is actually very common. Then notice that if lambda I is negative and far away from 0, then for like relatively small t, this coefficient is going to be negligible, right? And so a very typical procedure would be to say, just compute the first couple eigenvectors, like the ones that are closest to 0, evaluate this expression, and just like truncate the rest of the terms, because for large t, that's going to be good enough anyway. Yeah? In fact, if you're really sneaky, then you come up with some other approximation procedure to sort of approximate the difference between those two things. Okay, so all this is to say that essentially it's quite straightforward to solve a differential equation if you know the eigenvectors of your matrix. By the way, if you want to return to the f equals ma example, a better thing to do would be to not apply this reduction and just to stay in the world of second order ODE. Notice that basically my whole argument here is basically the same, but now I'll get a c double prime and a lambda squared there. Yeah, and so that's really the better thing to do. So that's my bet. Yes, I mean. I can. That's a good question. Here's a sort of smart ass answer to your question. So in particular, here's the thing that you can do. And actually, mathematically, this is perfectly well justified, but it feels uncomfortable, which is the following. Suppose, so one thing that we can certainly do at every time, just independently from every other time, is take y of t and write it in the y basis, right? And that's going to lead me to a bunch of coefficients ci. But it could be, I think like Hamid's intuition is right, that like for whatever reason, those things are not differentiable. They like wham all over the place. They have discontinuity, like who knows, right? So here's the way that you can justify this is as follows. You can say, suppose it were differentiable, right? Well, if the CIs were differentiable, this argument is certainly true, right? Now here's the thing that you can do. You can take this expression and just double check that, okay, let's say that I wrote the following. I said, okay, possibly, I hypothesized that the solution of my ODE is equal to Ci of 0 e to the lambda I t yi, like that, right? Well, I can basically just double check that this thing satisfies the ODE that I started with. And now a posteriori, I'm good, right? Because the ODE, this one certainly has a unique solution. Yeah. So this is a sort of a circular argument. It kind of says I hypothesize it's differentiable. Under that hypothesis, it must take this form. Now all that's really left, if you want to be careful with your argument, is to double check that the thing you wrote down actually satisfies the equation. Yeah, good question. Keeping me honest. All right, any others? Fantastic. Incidentally, one thing that you can do kind of generically is if I have a nonlinear ODE, so for example, like y prime equals f of y, like that, right? Well, now it kind of feels like, bananas, I can't use this whole machinery I've built up here. That's actually not entirely the case. One thing that I can do is write a Taylor series for f, right? So this is like approximately equal to like, what? Like some f of y0, maybe plus df, like the Jacobian of f, at y0 times y. This is what we call an inhomogeneous linear ODE. And it turns out there's basically a change of variables that can kill that constant term there. We're going to return to this later in this course. And then, so at least for like small t, you can still use this formula. It's just that every once in a while you got to update your df. And that leads to a whole class of integrators out there. I believe these are called exponential integrators. Okay. So this is yet another thing that you can do with eigenvectors. Here's a third. So let's say that I have a symmetric matrix, and moreover, it's invertible. Okay? So let's say that A is symmetric. So in particular, it emits a full set of eigenvectors. Okay? So A transpose equals A. And now I write down a whole basis. A, I don't know, maybe we'll use the same notation as before. Yi, like that. And now, let's say that I want to solve Ax equals B. Right? So like, I want to solve equals B for X. Right? Now here's a fun thing. If my matrix is symmetric, then actually the y's are orthogonal to each other. Right? So in particular, I can write X is equal to the sum over I of X dot Yi times Yi, like that. Right? Because these are all mutually orthogonal, and I can normalize them. So in that case, what do you think I'm going to do? Well, I can also write B in the same basis, right? So this is like that. B dot Yi times Yi, like that, right? And finally, what is A times X? Well, if I multiply both sides of this expression by A, I'm going to get that this is the sum over I of lambda I X dot Yi, like that. So by basically exactly the same trick we use for differential equation, right? If we want Ax equal B, then these two expressions have to equal one another. Does that make sense? So notice that from this thing now, well, what do I know? I essentially have two things that I've matched together, like that. And I conclude that X dot product with Yi is equal to B dot product with Yi divided by lambda I. Does that make sense? Okay, so in particular, remember, I'm trying to solve for X. So I can do that, right? Because X, by the way, this is a good way to solve that homework problem involving functions that preserve distances. So X is equal to X in the Y basis, so X dot Yi times Yi, like that. Right? This is just writing it in the orthonormal basis. But now I have an expression here, right? So this is B dot Yi divided by lambda I Yi. And this is just a formula, right? Because I know the B's and I know the Y's and the lambdas. So this is all to say, like basically, hopefully the sort of conclusion that you guys are drawing is if I know all the eigenvectors of a matrix, I know a lot about that matrix, right? I can invert it. I can solve differential equations. I can solve these squares problems. All of these things are pretty straightforward once I know this particular thing about the matrix here. Okay? Yes? If I have a zero eigenvalue, do I have any business solving Ax equals B? No, because my matrix is not invertible. Yeah, good question. Okay. So for our final example, we'll do something slightly more involved, and then we'll call it for the day, which is going to be something I'll call spectral embedding. This is very common. Actually, I think people in unsupervised machine learning, at least maybe 10, 20 years ago, this is sort of the basic technique that was used there. It goes by many names. Diffusion maps is one of them. Let's see, spectral clustering also ends up looking pretty much the same as this thing. And essentially, our task is going to be as follows. So let's say that I have a big collection of objects. So for example, this database of photographs, and I'm just trying to organize it. So like, I want to lay it out on a straight line. Right? That's a pretty straightforward thing to do. And similarly to our last couple things, laying it out on a grid is going to be basically very similar. So if I want to take all of my data points and lay that out on a line, what could I do? Well, essentially, there's like some unknown variable xi associated to each of my data points that is like its position on the horizontal axis, right? And I'm going to use that to maybe order my data points or something like that. Okay? So maybe I go through my big data set, like here it's a bunch of photographs, and for every item on my data set, I measure its similarity to every other item in the data set. Right? So like distance, like e to the minus distance would be a very rudimentary one. Maybe I like, run it through my favorite vision language model or whatever, and then like I try to measure the similarity of two images. And basically what I cook up is some matrix W, which has a bunch of positive numbers, and those numbers, let's be careful, the W's are large when the two items are similar. Does that make sense? Like, hopefully you guys could all engineer. And we're actually not going to make very many assumptions on W, just some positive matrix. Okay? We are going to make one assumption is that it's symmetric, so that if A is similar to B, B is similar to A. Cool? And our output for this problem is going to be an embedding on the real line. So basically, I'm going to assign to each item in my data set some number so that if they end up in similar places on the real line, then they somehow have similar structure according to W. Does that make sense? This is like goes by a lot of different names, like embedding problems. PCA is actually quite similar to this. We'll see. The difference here is that we don't have access to a bunch of points we're projecting down. We just have this similarity matrix. It's like a little more generic. Okay? All right. So what are we going to do? Well, as with most problems in this class, we're going to start with our sort of application-oriented thing. We're going to try and write it as an optimization problem, and then convince ourselves that eigenvalues are the way to go. Okay? So in particular, we've decided basically to every point in our data set, we're going to assign it some number xi. So our unknown variable is just a vector of values x, one per point, that's going to give us its position in this nice layout of my data set. And remember what I want. I want that if 2 points are nearby, sorry, 2 points are similar, then they end up nearby in my embedding. That kind of story makes it sound familiar? Okay. So here's one way that I think you could express such a thing, which is as follows. So we've got a bunch of x's. And basically the only thing we know how to do so far in this class is least squares. So we might try to use that language to set up our optimization problem here. And thankfully we can do it. So one thing I could do is say, well, if 2 points have a big W, then I want to penalize if they get assigned faraway positions. So in particular, I might make my objective function something like this. The sum of wij times xi minus xj squared. Does that make sense? Like, what is this saying? It's saying that if xi and xj are far apart, and if w is large, meaning that they're similar, something has gone wrong, because I'm trying to minimize my objective. Notice this is already a little different than our last eigenvalue problem, which we were maximizing. Okay? Now, let's say I stopped here. What's the minimum of this objective function? Yeah, on. Yeah, just make x's all the same. Like if I take all the xi's equal to 0, then this objective is 0, and this thing is happy. So that's not a very exciting solution. So I might like start adding constraints to this problem to make sure I don't get the trivial solution. Right? So one thing I might do, unsurprisingly, given the rest of this lecture, is just say they square sum to 1, right, to eliminate the solution where they're all 0. Is that enough? Was that? No, why not? Yeah. So in particular, if I took all of the xi's to be 1 over the square root of the number of data points, right? Then notice that the norm of this vector is 1, and I still get a boring embedding. So sadly for our problem, it doesn't fall into the category we had before. We need another constraint, namely that maybe the sum over the xi's is equal to, I don't know, 0. Notice that kind of, these two constraints together are enough to invalidate this constant thing, because now you need at least some things on the left of 0 and some on the right. Yeah? We're going to use a nice notational convenience that's going to become common in this class. This is the Blackboard 1. I have bad handwriting, but basically it's just the vector 1, comma 1, comma whatever 1, right? So a way to write our constraint is that the dot product between 1 and x is equal to 0. Cool? This problem, it turns out, have non-trivial solutions. So now we're in good shape. Okay. So our goal is to show that this problem can once again be solved with an eigenvalue problem. Now it's not entirely obvious because we now have two constraints. So there's a little bit of work that we have to do. So the first thing we'll do, kind of similarly to before, is simplify our objective function a bit and write it in terms of that nice, like these matrix W. Sorry. So let's do that. So in particular, so this is the problem we want to solve. We have the sum over ij, wij, xi minus xj squared. This is screaming out to us to expand the square, because basically this whole class is just high school algebra. Xi squared minus 2xi xj plus xj squared. Okay? Notice in this case the x's are scalars, so we don't need like a norm or anything like that. Okay. Now, here's a kind of a nice thing. So notice that like here and here, because remember that the W is symmetric, what do I really have? I have like something that looks like the following. So it's like sum of wij xi squared, like that. Right? So I can kind of separate off my sum and say that this is the sum over I of xi squared, sum over j of wij, something like that. Does that make sense? So let's give this thing a name. Let's say that we're going to call this number a sub I, which is like the row sums or the column sums of W, because it's symmetric. Right? So a different way that I could write it is to say that A is equal to the matrix W times the vector of all ones, like that. Does everybody agree that that's like just computing row sums? This piece of chalk is tiny. I don't know why I'm like determined to finish it off. Okay. So in particular, if we plug this guy in, notice that this term and this term are the same by symmetry of W. So I can write my expression in a nicer form. So this is 2 times the sum ai xi squared. Now this is just a sum over I, minus 2 times the sum wij xi xj. Everybody agree with me? Okay, fine, I'll switch chalk. Okay. To a different tiny piece of chalk. Okay. So our goal here is to basically write this thing in nice matrix notation. I'm going to define a second thing. I'm going to say that capital A is the diagonal matrix whose elements are the little a's. And why do I do that? Well, that allows us to write our objective function in a really slick way. This is just 2 times x transpose big A minus W x. You guys see that so far? I'm starting to skip steps because I think like hopefully you're pattern matching by now. Okay. Right, so notice now we can kind of vectorize our optimization problem. We have min of maybe 2x transpose A minus W x, subject to the constraints that the norm of x squared is equal to 1, and 1 transpose x is equal to 0, which is just a reshaping of the problem we had before. Okay? Now, what is this screaming out for us to do? Because we keep following exactly the same pattern in this class. Lagrange multipliers. Excellent. So let's do that. All right, we only got 15 minutes, so I'm going to be brave enough to use the board in the back. We're committing to our last blackboard for the day. Okay, so what is our Lagrangian in this case? Well, it's 2x transpose A minus W x, like that. And now we have 2 Lagrange multipliers. 1 minus x squared. But now we need a second one, mu, times the sum of x, like that. Okay? So sadly for us, when we take the optimality conditions with respect to x, we don't get what we wanted, right? We don't get ax equals lambda x, right? We get something slightly more hairy than that. So if I differentiate with respect to x, and well now I'm going to get 4a minus w x. Notice that this is a symmetric matrix, so this is the right expression. Okay, we've got minus 2 lambda x. But now, what are we going to get? We're going to get plus mu times the vector of all ones. So we're like almost at an eigenvalue problem. Like, it feels like we could get an eigenvalue problem, but we're not quite there. Any ideas? How can we address this? Here's kind of a fun, sneaky thing that we can do. What is the one fact that we know? We know that x sums up to 0, right? So in particular, one thing that I could do would be to pre-multiply this expression by x transpose. Or not by x transpose, rather by the vector of all ones, right? Because then I could at least get rid of this term here. Okay? So maybe just speculatively, let's give that a try. We're going to pre-multiply both sides by the transpose of the vector of all ones, like that. Okay? So what am I going to get? I'll get 4, 1 transpose A minus WX minus 2 lambda 1 transpose X plus mu times, what's 1 transpose 1? If you think about it, it's just n, like the size of the problem, right? Because it's 1 plus 1 plus 1 plus 1 plus 1, yeah? Well, this feels ugly, but I claim it's actually quite nice. So first of all, what is 1 transpose X by definition? Louder. 0. Third time. 0. Thank you. Oh my goodness. Okay, so this is just 0. We're almost done, I promise. This one's a little bit sneakier. So let's take a look at this expression here. This is the row sums of A minus the row sums of W. Do you see that? Or I guess the column sums the way I've written it, but they're symmetric, so whatever. What are the row sums of A? Well, A is diagonal, so it's just the individual elements of that vector A. What are the row sums of W? Well, by definition, they're the elements of that vector A. Yeah? So what is this product here? Also 0. Yeah? So, okay. There's 0 minus 0 plus mu n. So what we conclude is that actually mu, we got lucky, is equal to 0 for this particular problem. Okay? So what does that allow us to do? Well, we plug in mu equals 0 there, or here rather, and we can conclude that 4a minus w x is equal to 2 lambda x, which of course is an eigenvalue problem if I just divide both sides by 2, like that. Cool? Isn't that sneaky? That's kind of a fun trick. By the way, to my students Leticia and On, who I told them something wrong like 3 months ago, notice that this proof is basically the same as the math mistake I made in a much more complicated case a couple months ago. In any event, am I done? No, because I need to decide which eigenvalue I need. So what do? Well, just to continue our pattern one more time, I'm going to plug in this expression into our objective function and then figure that out. So in this case, remember I have 2x transpose a minus w x, like that. Now I know that 2a minus wx is lambda x. So in particular, this expression is lambda. Does that make sense? Because x has norm 1. Now, our problem is a minimization. So what does that mean? Well, that means in this particular case, lambda is the smallest, I have to be the tiniest, but careful, non-zero eigenvector of, or eigenvalue, whatever, of 2a minus w. Obviously that 2 isn't doing anything, but whatever. Does that make sense? Notice I have to say non-zero because, in fact, it's quite obvious that a minus w has a 0 eigenvector. Do you see that? What is that eigenvector? The vector of all ones, right? We actually showed that earlier. Okay. So this is yet another application of eigenvectors. I think it shows up a lot. Like if you read research on things called diffusion maps or other embeddings, like what are some of the other embeddings people care about? Like these assorted spectral embedding algorithms, all of them boil down to some version of this proof here, where you essentially add all these different constraints, you end up with an eigenvalue problem. Typically, if w is positive definite, then you actually end up with the second smallest eigenvector of w. In graph theory, this is called the Fiedler vector of your graph. This, I think, by the way, this matrix A minus W, what is it? So W contains a bunch of like similarity values between things. And then A is sort of the sum of all the similarities between a given object and everything else. So like kind of intuitively, what is this thing doing? It's kind of subtracting off, like it's looking at elements of X. It's looking at all the guys that are similar to X, kind of averaging them together and then like subtracting off X. Does that make sense? Like it's taking a weighted sum of all the X's, and then it's sort of this diagonal scaling with the same weights. This object has a fancy name. If you take my other course, we're going to study it for about 6 weeks. It's called the Laplacian matrix. Right? So in particular, if you have a graph, let's say that W is the connectivity of a graph. Right? So it's like a 1 anytime two vertices share an edge. Right? Then what is this matrix? Down the diagonal, it's the valence of the vertex, and here, it's just got a 1 anytime there's an edge. This is a really, really nice matrix. It basically approximates the second derivative of a function, and its eigenvectors tend to be beautifully, beautifully structured. So if you like reading about this kind of stuff, the object that you should look into is called the graph Laplacian, and that's basically what we just derived, is the graph Laplacian for a graph with generic edge weights. Cool? Okay, so for once today, I promised we'd end early, and I think we actually will. So in our next lecture, what we'll do is hopefully I've convinced you that eigenvectors are useful, A, and B, that like they really can be understood from this optimization kind of framework, that essentially most eigenvalue problems come from either wanting a really nice basis for the space from your matrix, like the ODE problem and the matrix inversion problem we wrote down, or they come from an optimization problem with a quadratic objective and a single quadratic constraint. Those are basically the two places these things come up. Right? And I think that really that's like a much nicer way to think about eigenvectors than just like this fun AX equals lambda X thing, and like for some reason that's what you're looking for. Okay? So in our next lecture, essentially we're going to start, probably where I should have started was defining, or unknown, but I think we all know what an eigenvector is. Essentially we're going to ask the question of what matrices have eigenvectors. Right? This, I think, often gets elided in undergrad linear algebra class. And then we'll talk about algorithms for solving eigenvectors, and we'll see they're actually very straightforward. They just involve multiplying by your matrix a bunch of times. Then the lecture after that, we're going to derive a really fancy algorithm for eigenvector computation, which gives you all of the eigenvectors at once in a matrix. And it's so beautiful. If you want to derive it at home, here's your challenge. Here's all you do. You take a matrix, you factor it as QR. Conveniently, we just did that. And then you replace that matrix with RQ. 2 lines of code, and you just iterate that. And what you will find, at least if your matrix is symmetric, is that R will converge to a diagonal matrix of eigenvalues, and Q will converge to the set of eigenvectors. This is entirely not obvious, and we're gonna justify why in a few lectures. Okay? We'll maybe save your question for after class. So in any event, you guys have a delightful Wednesday afternoon. I'll see you on Monday. Please start your homework if you haven't already, and that's all.